We've got two functions, f of x, which I will draw in blue. That's a straight line. You know what that looks like. X plus 2, straight line, slope of 1, that's its graph. You've also got g of x, which I'll put a green box around, and you can have an image of that in your head. That is your square root graph. Not square root graph, that is your absolute value graph. That looks like that. So the domain and range of both of them, well, this one's domain is everything, and this one's domain is everything. Now we're going to get into some new language. We're going to find out what it means when it says write an explicit equation. An explicit equation means that you want to write it in terms of x. So this, in B here, this is not an explicit equation, because this is in terms of f and in terms of g. All I would have to do to change this to an explicit equation is instead of f of x, I could replace that with x plus 2, and instead of g of x, I could replace that with the absolute value of x. So now that this is in terms of x only, we would call this an explicit equation. And we want to find the domain and range of this graph. So we're going to have to add those two graphs together. Because right now, the way that this is written, it's kind of weird with the absolute value. Like, you don't know how to combine your like terms. It's pretty obvious that the domain is still everything, because there's no x values that you're not allowed to put in. But it's not obvious what the range is. So what I'm going to do is I'm going to add the two graphs together. And we're going to see what happens. We can add the two graphs together, or you could just do it like adding the two graphs together is sort of like doing a table of values. We could just figure out what x is and find out what the resulting y value or h of x would be. Like if I plug in 0, can you see that you would get 2? If you plugged in 1, this would be 3, this would be 1, you would get 4. If you plugged in 2, you get 4 plus 2, you would get 6. And you might notice this seems to be a pretty straight line, which it is. And interestingly, so I'll just write it in here. What did I plug in? I got 0 and 2, 1 and 4, no, 5. 1, no, 4, yeah, that was good. 2, 2, came up to 6. But notice what happens when you plug in -1. -1 plus 1, -1 plus 2 is 1. -1 in the absolute values would be +1. So this will become 1 plus 1, which is 2. And notice what happens if you plug in -2. -2 plus 2 is 0. Absolute value of -2 becomes +2. You get 2 again. This ends up being a flat line straight everywhere to the left. Because if you put in a negative number, the absolute value makes it positive, and it sort of counteracts that other negative x that goes before. So the range, again, the domain of this one was still everything, but now our range is y is bigger than or equal to 2. Okay? And before we get to C, I'm going to introduce to you.
You wrote a 0.
Yeah, I wrote a 0. That is no. Wait for it. Oh, we're gonna strategically. Very nice. Y is greater than or equal to 2. Now before we get to part C, I'm going to introduce to you something that does come up in the AP calculus class, something called piecewise notation. And when I look at the final blue graph, doesn't it look like two different lines that are put together? And what piecewise notation says is sometimes when we have two different graphs that are put together, we can actually write each equation separately as one piece and a second piece. That's why it's called piecewise notation, because you're breaking your graph up into different pieces and saying each of them on their own. And the most common piecewise notation graph is actually one that you start with the most is the absolute value of x. Can you see the absolute value of x? The V graph is just two straight lines. So in piecewise notation, we would write the absolute value of x like this. We do these squiggle brackets to say that we're going to have two different pieces. And one of the pieces is just the x graph. And the other piece is the negative x graph. Can you see the negative x graph and the x graph put together? But we don't have, right? I'll try to color code this. This in green is my absolute value graph, right? This in blue, no, that's not blue. Try again. This in blue is my negative x graph. And this in purple is my x graph. Can you see that the green graph starts off being the blue graph and then it switches to be the purple graph? So if we started off, maybe I'll even write them in that order. It doesn't matter. But if I wrote that graph first and this graph second, in a piecewise graph, you write the piece and you say the domain that you use that piece for. So we had the blue graph until we got to 0. So we had when x was less than or equal to 0, we used the blue graph. And then we switched to the green graph, or the purple graph, when x was bigger than 0. And this is called piecewise notation, where instead of writing the whole equation, you break it up into its pieces. So what does that mean for h of x? Right? Originally we had h of x to be x plus 2 plus the absolute value of x, right? But since this is a piecewise graph that switches, if I chose x less than or equal to 0, then the absolute value of x is actually equal to negative x. And the equation would become x plus 2 plus a negative x. And if x is bigger than 0, then I can change the absolute value of x to just x. And I would get x plus 2 plus an x. If I simplify this, this just becomes 2. Did we notice it was always 2 when x was less than 0? And here, x plus x, this will be 2x plus 2. We got a straight line with a slope of 2 when x was bigger than 0. So when I write it as a piecewise equation in this box right here, can you see that in the graph? That it was always equal to 2 when x was less than or equal to 0. And then it was a straight line. Hey, look, this has an up 2 over 1, up 2 over 1, a slope of 2, a y-intercept of 2. It's this line, but we only have a piece of that line just when x was bigger than 0. So when a graph can't be graphed all at once, we could put it together as a piecewise graph. And you could put half of a parabola with a straight line coming off of it and make it a new graph. So you could have all sorts of new graphs as a result. And you don't have to be limited to two pieces. You could take part of an x cubed graph, then add a log graph to it, and then add a sine graph after that, and have this weird looking graph in the end with three different pieces. So that's all that piecewise notation is. But piecewise notation, if we use it, and especially we use it for absolute value of x, because it's equal to negative x when x is less than 0, right? Because if you plugged in -2 into negative x, you'd get negative 2, which would make it positive. And that's what the absolute value does, makes something positive. And if it's bigger than 0, the absolute value signs don't really matter. It just stays whatever it was. So that's what the piecewise notation is. But it can be really helpful, and we'll see it in part C. Part C, it says, write the explicit equation for P of x, determine its domain and range. It's going to be easier if we use the piecewise notation. Okay? Because either A, you have to multiply a bunch of values to see what this graph looks like. But if you have the actual equation, it might be easier. So, let's look at C. The explicit equation, well, one of them was x plus 2. The other one was the absolute value of x. With it written like this, the best you could do is do a table of values and see what you get. But if we write this in piecewise notation, we know that when x is less than or equal to 0, absolute value of x is the same as negative. And we know that when x is bigger than 0, the absolute value of x is just x. If I simplify this, here I'm going to get negative x squared minus 2x when x is less than or equal to 0. And here I'm going to get x squared plus 2x when x is bigger than 0. And this reviews a little bit of chapter 1 and a little bit of a grade 11. Those are both parabolas. You have one parabola opening up, one parabola opening down. I am going to graph this one in blue with a dotted line, this one in green in a dotted line, and then draw the final one in purple that shows both pieces. Okay? What I liked about the top equation is it was in factored form. Then I can use chapter 1. I would know the x-intercepts. I would know that in my blue graph, I have an x-intercept at 0 and at -2. I would know from grade 11, this is a parabola that's negative, which opens down. So I would know that it would have its vertex in between there at that point. I could even plug in -1 to find out that it's at 1, or maybe because I know my a value is 1, it has to go up 1 over 1. And this would be the blue graph, oops, with a dotted line. That's the parabola of the blue graph. Similarly, the green one, in factor form, it has the exact same x-intercepts, but my green graph is positive. It's going to open up. I could do the same thing and figure out that its vertex is at -1, and its graph opens up like this. So now I've drawn both graphs in their entirety with a dotted line. The last thing I have to do is draw the final graph with the right pieces. So I'll take out my purple pen. I'm supposed to draw the blue one when x is less than or equal to 0. So I go to 0, and everything less than it, that's my blue one. And then when x is bigger than 0, I'm supposed to draw my green one. It kind of looks like an x cubed graph, but an x cubed graph, if you touch the bottom here, you wouldn't hurt your finger. This one is sharp. You cut your finger like out. It's really pointed. Don't. These graphs are dangerous now. Be careful. It's a very sharp point right there at the bottom. But that is a very accurate graph, right? What was the technique that we learned yesterday? You would take your original graphs and just multiply x coordinates, multiply y values, and get a whole bunch of them. It is not obvious that when I take a line and multiply it by an absolute value graph, that I would get that picture. Not obvious at all, is it? So I find that if you can find the explicit equations, and this one you have to use piecewise. By the way, I've never seen a piecewise question on your provincial exam. They would usually give you easier ones. So this would, but you do need to know piecewise stuff for the AP Calculus. You'll relearn it or learn it again in that course, so it's not bad to see it. It's not crazy hard. It's just saying that some graphs you can put together with two different parts. Okay, did it ask for domain and range? Yes, okay. Well, it's domain, I'll do purple, because my final graph is purple. Its domain is everything. There's nothing not allowed. Its range is everything. And we have our final graph. So we're going to find that if you have the actual equations, some questions, they're just going to give you graphs. But some questions, they give you the actual equations. If you have the actual equations, then figuring out the explicit equation will probably be even easier to graph. Okay, questions you can circle for this one are 3, 5, and 10.